Hi everyone, welcome to CS 3500 Numerical Methods. So before we start the concept of this course, let's review some useful background knowledge from calculus. Okay, so first, intermediate value theorem. Suppose f is a function satisfying the following. First, f is continuous. So what does continuous means? So continuous means you can draw the curve without lifting your pencil from the paper, right? The formal definition, f is continuous at a point A if f is defined at the point A and the limits at the point A exist. It means the left side limit and the right side limit agree, okay? And then the function values must equal to the limits at that point. Then f is continuous. Okay, so we have f is continuous on the interval a, b. Either f of a is positive and f of b is negative, or f of a is negative and f of b is positive. So we want f of a and f of b are of different signs. Okay, so this is the two assumption. The conclusion is there exists a number c between a and b such that f of c equals 0. So let me draw some picture here. So let's say we have a and b here. Let's say f of a is negative, so it's below the x-axis, okay? And let's say f of b is positive. Then because f is continuous, then there must be a point c such that f of c equals 0. So it must cross the x-axis somewhere. Or the picture could be we have a and b, we can have f of a is positive, f of b is negative, and then we have the function is continuous, so maybe it crosses the x-axis at this point c. Or it is also likely that we can cross this several times. It is possible. Or maybe we can cross it infinite many times. So far, so good. So we know there is at least one number c such that f of c equals 0. Okay? So that is the intermediate value theorem. You can imagine, you can make up some story to, let's say you're standing right here and your girlfriend is standing right there across the street. How do you find your girlfriend? You must go across the street, right? You cannot jump from here to there. No, we have to cross the street. And you might cross the street a couple times, or you can, your trajectory can look like that, right? So that is intermediate value theorem. We don't know where the c is. We just know there exists a c such that f of c equals 0. So far, so good, everybody? Okay, next. Mean value theorem. Suppose f is a function satisfying the following. First, f is continuous on the closed interval a, b. Second, f is differentiable on the open interval a, b. Then there exists a number c between a and b such that the derivative at c equals change of f over the change of like b minus a. Okay, so what does that mean? Well, if we draw the picture here, so let's say this is a and this is b. Okay, let's say this is f of a, this is f of b. What is f of b minus f of a over b minus a? This is the slope of the secant line passing through the two endpoints. Okay, so this is change of y over change of x. This is the slope of the secant line passing through a f of a and b f of b. Okay, and this theorem, the mean value theorem, tells us that if the function f is continuous and differentiable, let's say like this. Then there exists a point C such that this tangent, the slope of the tangent line at that point C, okay, equals the slope of the secant line passing through the endpoints. So this is the slope of tangent line at C. We can also have the picture, we can have A here and B there. We can have our curve look like this. Then maybe there are several C such that the slope at C equals to the slope of the secant line. It is all possible. Or maybe we have F is a straight line. Then there are infinite many C such that the slope at the point C equals the secant line slope. Right? So we don't know how many C there. We just know there exists at least one C which can satisfy this condition. Right? And we don't know where the C is. It could be, it really depends on the function f, okay? We don't know the location of the C, but we know there exists at least one C such that the slope of tangent line at the point C equals to the slope of the secant line passing through the two endpoints. So far, so good, everybody? Okay, so we usually use the intermediate value theorem and the mean value theorem together to show an equation has exactly one real root. Okay, so let's see here. Okay, so look at this function. We want to show this function has exactly one real root. So first, we want to show there is at least one root. Well, and this guy we will use intermediate value theorem. Okay, so here, so for this kind of problems, there is a pattern. I mean, there's ways or steps of how to solve it. Okay, for the portion that is specific for this problem, I'm gonna use the green color. Otherwise, I will use the orange color. So which means if you see the similar kinds of problems with a different function, you only need to change the like the sentences or the parts of the green parts. Okay, green color parts. Okay, so first, at least one root. Well, first we want to check the hypothesis of the intermediate value theorem. Is f continuous? Yes, because f in this case is polynomial. Polynomial is continuous everywhere. Okay, second, we want to find a number such that f of that number is positive. We also want to find a number such that f of that number is negative. And here, because we were given an interval, so it's natural to check the endpoints of this interval. So let's check 0. If we plug in 0, we get f of 0 is -2. Oh, see? F of 0 is -2. Oops. Zero equals, here f of 0 is -2 and it's negative. Okay, and we plug in 1. When we plug in 1, we get 1 plus 7 minus 2. Well, that is 8 minus 2, 6. That is positive. So we need to find points. F of that value is negative, and we also need to find a point such that f of that point is positive. Okay, so this is the hypothesis of the intermediate value theorem. Then we can say by intermediate value theorem, there is at least one C such that f of C equals 0. And you can also say there is at least one C inside the open interval 0, 1, such that f of c equals 0, right? So the function has at least one root. Okay, so we have at least. We also need to show at most. Okay, at most one root. Sorry. At least is greater equal. At most is less than equal. Okay? So then when we combine those two steps, we get exactly one root. So how do we show at most one root? We'll use mean value theorem. Okay, sometimes we can also call Raleigh's theorem. Okay, so mean value theorem. First, we need to check f is continuous, and we already know that. And we also need f is differentiable. Well, let's figure out the derivative. Well, the derivative in this case, let's see, is 5x to the 4 plus 7. Right? And you see this guy is continuous. Furthermore, because x to the 4th is greater or equal to 0, when we add 7 to it, this guy is always positive. Right? Okay, so we can also say f is differentiable because the derivative exists everywhere. Alright, so how do we prove at most one roots? We prove by contradiction. Okay, suppose we have like more than one root. Okay, so suppose a, b are two roots. Well, that means f of a equals f of b equals 0. Alright, then by mean value theorem, there is c inside, there exists a c such that f prime of c equals f of b minus f of a, and b over b minus a, because the numerator f of b equals f of a, so we get equal to 0. Wow, this is a contradiction to our, so this is a contradiction to f prime is positive for all x. Okay, so because we have a contradiction, it means whatever we assume is false. So there can be two roots. Then there is at most one root. So f has at most one root. Okay, finally, I don't have enough space. So finally, we say combine 1 and 2, f has exactly one root. So far, so good, everybody. Okay, so so this is the complete step of solving this kind of problem. When you see a new example, you actually just need to change the green parts. Okay, so you're gonna pick a point such that f of that point is negative. You pick a point such f of that point is positive, and you also need to differentiate. But here, you either get always positive or always negative. Then later on, we can also get a contradiction. Okay, so we learned this in Calculus 1. Okay, in sessions 4.6. Okay, so let's continue. Next, Taylor formula with remainder. Okay, so this is from Calculus 2. If f is sufficiently smooth, it means we have the f derivatives. Okay, so it depends on our formula, because if we might need n plus 1 derivative, so it means all the nth derivative exists, okay, up to the order we want. So if f is sufficiently smooth, it can be represented by its Taylor polynomial, which is in the powers of x minus a, plus a remainder term. Okay, so f of x equals f of a plus f prime of a x minus a plus f prime prime of a over 2 factorial x minus a squared plus the nth derivative over n factorial times x minus a to the power of n. So this is the nth order. So this is the nth order Taylor polynomial. Okay, we also have the Taylor series. Well, Taylor series, you just replace by dot dot dot. Okay, there are infinitely many terms in the Taylor series. So this is in chapter 9, okay, of our calculus 2. But when we talk about this guy in chapter 9, okay, we didn't talk about the remainder. We just say, oh, f can be approximated by the nth order Taylor polynomial. Actually, if we consider the remainder term, okay, then this guy is not only approximated, this guy could be equal. Okay, so f of x equals the nth order Taylor polynomial plus the remainder term. What's the remainder term? The remainder term is very similar to the next term in the list. The next term in the list should be n plus 1 derivative over n plus 1 factorial times x minus a to the power n. But this is not exactly the next term in this list, because you look at here, inside, we evaluate at z. We don't evaluate at a. So the next term in this list should be evaluate. So the n plus 1 derivative evaluates at a over n plus 1 factorial times x minus a to the power of n plus 1. Okay, but the remainder term is similar to that, but except here we don't evaluate at a. We evaluate at z for some z between a and x. Okay. So far, so good, everybody. So we don't have a fixed z. We just know z is between a and x. And then this is the remainder term. We get equal. Okay? So, and we have the table for Taylor series. So for the function 1 over 1 minus x, the Taylor series is sum k from 0 to infinity, x to the power of k. The interval of convergence is minus 1 to 1. Radius of convergence equals 1. Do you still remember what is the interval of convergence? Well, it's the set of values such that f is such that the Taylor series converges to f at that point. Okay? All right. So, and then you can see the next one, 1 over 1 plus x, is simply just like replace x by minus x. So we replace x by minus x, we get this new Taylor series formula. Okay, next. We have e to the x. Well, that's the formula of sum of x to the k over k factorial. And we also have the sine formula, cosine, and arctangent ln of 1 plus x. So far, so good. And for exponential function e to the x, sine and cosine, the interval of convergence is minus infinity to infinity. So the series converges to the function at all values of x, okay? At all points of x. All right, let's continue. So we can use Taylor polynomial to approximate some function. So let's look at the following example. Use the first three non-zero term of a Maclaurin series. Maclaurin series is just a special type of the Taylor series where the center is 0. Okay, so this is the Taylor series, but with the center A is 0. Okay? Alright, so let's see how we solve this problem. We know, well, this is exponential function, so we should better consider e to the x, right? E to the x, the Taylor series, is k from 0 to infinity, x to the power of k over k factorial. Well, so that is, well, we want to use the first non-zero terms. So it can be approximated using the first non-zero terms. The first term, when we plug in k is 0, well, remember, 0 factorial is defined to be 1. So the first term is 1. And then we have x, right? And then we have x squared over 2 factorial is 2. So this is the first non-zero 3 terms, okay? So first 3 non-zero terms. And now we can plug in e to the 0.1 is approximated by, we plug in x equals 0.1. So 1 plus 0.1 plus 0.1 squared is 0.01 over 2. So that is 1.1. Wow, 0.01 divided by 2 is 0.005. So this is the answer. So far, so good. How about e to the minus 0.25? Well, it's approximately by, we plug in x as negative 0.25. So negative square is positive, so 0.25 square over 2. And what is that? Let's see. So in our course, we will use calculator a lot. So let me just pick an online calculator to show you. Okay, so 1 minus 0.25 plus. I also hope you can calculate it with me, right? Also learn how to press the button. Okay, so we get 0.78125. So far, so good, everybody. Next, let's check our answer. So this is the good thing about this kind of problems. You can always check our answer to see whether we make mistakes, because we can plug in our calculator directly. Okay, and what's e to the 0.1? So let's see, where is the e? Okay, here. E to the 0.1 equals, see, 1.105 170918. 1.105 and then what is that? 170918. Can you see? It's so close. See, it's so close. So it means good. We're good. Let's continue to check the other one. So we have e to the negative. Let's see. So some calculator, negative and minus, they're different button. So and let's see whether this website they mean the same thing. Okay, yeah, they mean the same thing. So the answer is 0.7788007831. Okay, so e to the minus 0.25. But in your calculator, maybe they are different button. Okay, So you gotta be very careful. So you can see this guy is also close to our answer. And you may say, well, the e to the 0.1 is closer compared to the e to the minus 0.25. Well, remember the Taylor series? The center is 0. So if the value x is closer to 0, then the approximation is more accurate. So far, so good, everybody. And you can see, when we use this Taylor polynomial approximation, we only use the 4 basic operations: plus, minus, multiplication, and division. Okay, so that's the good thing, we can calculate by hand. So even though exponential function in general, without a fancy calculator, you cannot calculate the numbers. But with the help of the Taylor polynomial approximation, we can calculate by hand. Okay, so that's Cal 2, the Taylor series concepts. Next, let's introduce some concepts to describe whether our approximation is good. So this course is all about we use different numerical methods to approximate, okay, iteration techniques. So it's very important to figure out whether our approximation is good. That means we want to consider the error, okay? So if x is our approximate result, and the exact, so usually we don't know the exact result. So let's denote the exact result is x asterisk. Okay, then the error in using the approximated result is e equals x asterisk minus x. Okay, so x asterisk is the true value, and this x is our approximation. Okay, but in many situations, the sign of the error may not be known and might even be irrelevant. So we are more interested with the absolute error. So absolute error is the absolute value of the error. So which is the absolute value of the difference between the true value and the approximation. Okay, so and however, especially for the problems in which the magnitude of the true value may be very large or maybe small, then the relative error, or we can say percentage error, may be more important than the actual error. Well, let's say if I tell you the error, if I only tell you the error is 1, then we have no clue this is good or not. Well, if we tell you the approximation, well, is like 2000, well, the error is 1 is kind of good. But if I tell you x is 2, well, your error is 1, well, then the error is quite big, right? So sometimes not only we want to know the error, but we also want to know the relative error. Okay, so the relative error, RE, equals the absolute value of the true value minus the approximation over the approximation. Okay, why over the approximation instead of the true value? Because usually the approximation is easier to calculate. Okay, so that's why the denominator is the approximation. Okay, so the number x is set to approximate the true value to t significant digits. If t is the largest non-negative integer for which the relative error is less than 5 times 10 to the minus t. Okay, what does that mean? Well, let's say if the relative error equals 0.00057, okay, then this guy is like 5.7 times 10 to the 1, 2, 3, 4. So minus 4. But however, you see 5.7 is not less than 5. Well, then what do? We need to think about, okay, so this guy is, let's multiply by 0.1 and we multiply by 10 to the minus 3. Okay, so let me see how do I do it. Okay, times 0.1 times 10. Okay, then it means I'm just having the same thing, right? So times 5.7 times 10 to the minus 4. Now what happened? So 0.1 times 5.1 will give us 0.57 times 10 to the negative 3, right? We can combine the 10 and 10 to the minus 4. It gives us 10 to the minus 3. So now, this guy is less than 5, right? So now this guy is less than 5 times 10 to the negative 3. Good. So then we say the approximation is approximate the true value to 3 significant digits. Okay, so approximated to 3 significant digits. Is that okay, everybody? Yeah, so that is why if this number is 4.7, then it is 4 significant digits. But if this guy is 5.7, it's bigger than 5, then you have to shift one more digit there. So far, so good, everybody. Okay, let's look at example 3. Round of error. So round of error is introduced by shortening a number that has more digits than it can be represented. So consider the following addition problem. 0.99 plus 0.0044 plus 0.0042 with exact arithmetic. The result is 0.9986. Now compute the 3 digits arithmetic with different order. So 3 digits arithmetic, which means each step of our calculation we just include 3 digits. Okay, so let's look at the first one, right? We have, when we add them together, we get 0.9944, right? But because we want to keep 3 digits, so we only put down 0.994. And then when we add 0.0042, okay, what do we get? We get 0.9982, but we only keep 3 digits. So that's why we only keep 0.998. Is that okay, everybody? Yeah, so only keep 3 digits. This is 3 digits arithmetic. Okay, what if we do the calculation of the last 2 numbers first? Well, if we do the calculation of the last 2 numbers first, then we get, okay, that is 0.0086, right? 0.0086. But what do you do with the 6? We round up. So we get 0.009. Now we get 0.999. You see? They're different. So you can see this is the round of error. Yes. Different order of the addition sometimes might give us different answer. So this is the round of error. So far so good, everybody? Alright, let's continue. Okay, so we use the first 3 non-zero terms of the Maclaurin series to approximate e to the 0.1. Now answer the following. What is the absolute error of the approximation? Oh, first of all, let's find out. Okay, so our approximation. Oh, what is that? So we use x to denote the approximation. That is 1.105, right? And the true value, we can think of this guy, right? True value is 1.10517 0.0918. Okay, so keep this in mind. By the way, I hope when you watch these videos, you are taking notes. Okay, and sometimes when you watch the video, it's good because you can control the speed. You can pause at each step and think through the math, and then you can continue. And you can play the video a couple times. And I strongly recommend you, before you continue to work on the example, please pause the video and then try the problem first. And then continue to play the video and check your answers. In this case, you can have more practice, and this is a good way to learn. Okay, so our approximation. Oops, why did I press something? So the approximation is 1.105, right? What is the true value? Okay, the true value is 1.105170918. Right? You just copy it down. Okay, next. What is the absolute error? Okay, thank you for the absolute value, because sometimes, even though I don't remember, I use the approximation minus the true value, or I use the true value minus the approximation. But with the absolute value, it doesn't matter. Okay, the difference is the one who matter. Then I usually use the bigger number minus the smaller number. Then my answer is always positive. So the bigger number is 1.105170918 minus 1.105. Okay, it means all these digits are gone, so we have 0.001700918. So that is the absolute error. Okay? So part B, what is the percentage error or relative error? Well, percentage error or relative error. Well, we use our absolute error divided by our approximation, 1.105, and let's see what is that. Where's my calculator? Here. So 0.10. Let's go back. Okay. 0.000170918 divided by 1.105 equals, so 1.546769. Okay, so approximately by 1.54677 times 10 to the minus 4, right? Let's check it again. Yes, 10 to the minus 4. So far, so good, everybody? Yes. So I would say usually if you have your answer in 5 decimal places digits, then that's good. Okay. And let's see. So this is a percentage error. Okay. And then this guy, to how many significant digits is the approximation accurate? Well, this answer is less than 5, right? 1.5 is less than 5 times 10 to the minus 4. So 4. So that's why we say our approximation approximates our true value to 4 significant digits. So far, so good, everybody? Yeah, because here is 1.5. 1.5 is already less than 5. So we don't need to shift the 10 there, like our previous example. Just be careful. Like this case, if this is 5.7 bigger than 5, then you have to do something like this to shift, okay, 1 digit. So far, so good, everybody? Okay, so those are the review, and the next video we're gonna start session 2.1. All right, so see you soon. Bye.